Good evening, everybody. How are you all doing? Is everybody good? Yes? Yes? We're excited about flying? I sure hope so. So, my name is Trevor. I'm one of the original founding members of Project Talaria. So I'm just, first of all, I just want to say thank you to all of you for coming. We are so excited that we have so many people here to support us. We are so thankful to all of our friends and family who have probably seen us staying up late, losing sleep, maybe missing a lecture or two, maybe not. But we really appreciate all the support that everybody's been giving us, and we're so excited to be sharing with you all of the work that we've been doing. Before we get started, I'd like to hand it over to Liam McGill. He is the team manager of Aero Delft, the Delft Aeronautical Student Society, and I'll let him say a few words.
All right, good evening, everyone. First of all, glad everyone could be here. My name is Liam. I am, as Trevor said, the team manager of Aero Delft. Aero Delft was founded last year in September. The idea was to become an incubator for student aeronautical projects such as Talaria. We were with Talaria from the very beginning. We've had our ups and downs, but in general, I'm amazed. I am so proud of what we've been able to achieve so far. And I am absolutely, it's the same word again, pleased that I'm sitting on stage with these opening words. So without further ado, I'm going to give it back to the Talaria team, and I wish you guys a lot of fun in this presentation. Thank you.
All right, buckle up.
They say progress is inevitable. We are always advancing. We are always moving forward. They say vision is the path we follow. We see what is directly ahead. We anticipate what will come. But if we look around, how much is really changing? Where are we headed? If we all work on the assumption that what is accepted as true is really true, there would be little hope of advance. Maybe moving forward isn't enough. Maybe it's time to go up.
Ladies and gentlemen, thank you so much for coming today. I'm Philip Esler, the team manager of Project Talaria. I come from São Paulo, Brazil, one of the biggest cities in the world. And like many big cities, it has a huge traffic problem. In São Paulo, it's usual to spend 40 minutes in traffic. I've always hated spending so much time in the car, sitting, just looking outside and being bored. Well, then I moved to Delft, a quiet student city, and I fell in love with the Dutch biking culture. You can bike anywhere in 10-15 minutes. It's a bit of exercise, fresh wind, minus the rain, all is perfect. Holland is blessed by being a flat country and having very smooth pavement. In São Paulo, however, we do not have such good pavements. These are our bike paths. Not very safe. But also, São Paulo is huge. It doesn't make sense to bike from one side of the city to the next, like it is here in Delft, or in Amsterdam, or Rotterdam. It would just waste too much time going from one place to the other. Not to mention that it's full of hills. It would be way too much effort to go from point A to B. So what are the other traffic solutions since the bike is not feasible? Well, there are buses and metros. Buses are widely used already in big cities, but the problem is that the streets are saturated with vehicles, be it trucks, personal cars, taxis, or buses. In São Paulo, the fleet of buses can move 500 million people a day. And that still doesn't solve the problem. So naturally you would think, well, let's just go underground. There's more space there, we can use that. Well, metros are very expensive, they take a lot of time to build, and they're still congested. There just isn't enough space underground and above ground to move 20 million people in the city of São Paulo. And that problem is not unique to São Paulo. It is a problem that reoccurs in every major city across the globe. In 1903, the Wright brothers made the first powered flight. And they flew 37 meters, a mere 3 meters above the surface. Back then, people were skeptical that flight would become a thing of the norm. 100 years later, we have the 747 carrying 400 people halfway across the globe. Progress is fast and transformative. Now, that is the past, the present, and the future is being brought up by companies such as Paul V here in the Netherlands, Key Hawk, and Lilium. These companies have been pushing hard to develop new technology and at such an amazing speed that they think that flying with a personal device such as these will be possible between 2020 and 2025. That's how fast they're going for. And what does this dream look like, you may ask? Well, imagine with me that you're late for a meeting. You don't want to take your chances in traffic, so you take out your phone, press on an app, a flying device comes over to your house, you sit on it, and it takes you to your office. You arrive there on time and in style. Another area where these devices have a great potential is rescue operations in remote areas, where a large helicopter wouldn't be able to land. A smaller, lighter flying device can go, carrying essential equipment and a doctor. Another area which is quite likely going to be a big market for these devices is tourism. How wonderful would it be to have a bird's eye view of Rome, Venice, Dubai, the beaches of Rio de Janeiro? It would be amazing. The bird's eye view is no longer limited to the birds. When we start to talk about this dream, this future, in November 2017, we realized that we don't need to wait to join one of these companies to become a part of this movement. We can do it now as students. And that's when we created Project Talaria. Talaria, for those who don't know, are the sandals of the Greek messenger god Hermes, and they give him his speed and flying abilities. Since we started the project, we were joined by 40 students from every faculty at the TU Delft, and are also part of the Personal Air Mobility Initiative from the aerospace faculty, where we work with professors to develop and implement this new field into the bachelor's and the master curriculum. When we started this project, we had a bunch of ideas, and we can imagine a future for each and every one of them. All of them have their own potentials and their downfalls, but a future for each and every one of them is possible. But naturally, we had to pick just one. Ladies and gentlemen, I present to you the Hermes One.
Well, after all the hard work, it's so rewarding to see it all come together. It's really unbelievable the amount of progress we've been able to make in just 5 months without a single full-time student in the team, at least on paper. I'm David, the Chief Engineer of Project Talaria, and you're all here to meet the Hermes One. So I'm going to do just that. I'm going to present the device and all its subsystems to you. Talaria's vision for the future of air mobility begins with a quiet, intuitive, personal flying device called the Hermes One. Here are some of the features that you can expect from this device. The first is 30 minutes of flight time. Why 30 minutes? Because that's usually what people are willing to put into their daily commutes. And that's the upper bound that we want to set on a commute for everyday transportation. Next, we want 40 kilometers of travel distance. 40 kilometers is an upper bound for the average urban radius of the largest cities in the world. We want the device to be vertical takeoff and landing, carry a 90-kilogram passenger, be low noise, and aside from all these tangible requirements, we wanted a device safe enough to be used by everyone, that could be certifiable in a given timeline, and that could offer the experience of open-air flight. But hold on, I'm missing a very important requirement, and that is size. Size is really what sets us apart from the companies that Philip just mentioned. And let me show you why size is really such an important and driving requirement. To do that, I'm going to compare it to the Atlas device. It's on the other side of the spectrum. A much, much bigger device than ours. It's a human-powered helicopter. You might ask, why is it so big? And the answer is simple. It's human-powered, so it needs to be incredibly efficient. By pushing itself off from a very large chunk of atmosphere, the rotors can spin at very low rates, and its power requirements go down by a lot. So if we compare the size of our device with the Atlas in numbers, we see that our device is 2.6 meters in maximum dimension, while the Atlas is 46 meters. And this has direct consequences on things like disk loading, which is the amount of kilograms that each square meter of the disk has to hold. And Talaria, for instance, has to lift 16 times more weight per square meter of each rotor. And this has direct consequences on the power requirements, as we use something like 100 times more than the Atlas. The Atlas device was clearly designed for one purpose, and that was efficiency. But it's not really functional. I mean, it's quite hard to imagine something like this landing on a rooftop, something the size of a Boeing 737. And even if it did, in the same area, you could land 235 Hermes Ones. So you can see that for applications like ride-sharing, where instead of picking up an OV bike at a station, you pick up a Hermes One at the rooftops, it's really beneficial to be ultra-compact. Now, I'm gonna, as I said, walk through all the major systems of the device today. And the big question to answer first is, how do we take off? So here you can see the major systems exploded. The propulsion system is actually responsible for taking us off the ground. So what the main highlight of the propulsion system is that it's a coaxial rotor system. And what this means is, as you saw, that the three bladed rotors are spinning in the opposite direction. And this has several advantages over a single rotor helicopter. The first is a higher efficiency for the same area. So by stacking two rotors on top of each other, you can produce almost twice the lift for the same amount of area. The second one is that there's no net torque on the main structure. So if you're familiar with conventional helicopters, you'll have noticed that they all have this very recognizable tail. And what the tail is doing is it's counteracting the moment that the rotors exert on the main structure. But with a coaxial, you have two rotors spinning in the opposite direction, and their torques cancel, so you can remove a tail. The last advantage is a bit more difficult and unintuitive to grasp, which is why I wanted to do a demonstration of it. And I'd like to ask Philip to help me out with it. It's about gyroscopic precession, which is something that is a very big problem in single rotor helicopters, but is completely eliminated in coaxial systems. So what we're going to do now is we're going to spin this wheel, which you should imagine as a rotor for now. And what we create then is an angular momentum on the system, which can be expressed as a vector pointing in this direction. And I'm going to hold it with this rope here. And what the system wants to do is just fall down. So there's a torque which is pointing in that direction. And so what the system wants to do is something very unintuitive, which I can show you right now. So you see that the angular momentum vector is following the torque vector. So the angular momentum vector is pointing in this direction, and the torque points in that direction, and it's just continuously following it. It doesn't fall down. So how does this translate to a helicopter, for instance? I'll try to give you a clearer view of how it works. So it's finished. Okay. So now we have the rotor here, and I'm going to pull on this rope, and what you expect is that the disc tilts towards me, but what it does is it actually tilts towards Philip. So I can show you again what happens. So in case you missed it the first time, I'm pulling on this, you expect it to move this way, but because of gyroscopic precession, there's a 90-degree shift. And it does something completely unintuitive. So when you have a coaxial system, it really just behaves as if I weren't spinning it at all, because the angular momentum is zero. It cancels out. So it's really just as intuitive as if you hold it here. It just follows what is intuitive. So by removing a tail and the gyroscopic effect, our system has removed all cross-coupling and is much more intuitive to control. Now you might be asking, what is all this stuff in the middle? Well, that's the collective system, and it's responsible for setting the level of thrust. And the way this is done is you basically have a bottom collective plate, which is actuated up and down, and through the rods, this is translated into a rotation motion of the blades, which can basically set the level of lift of each of the blades individually, and therefore you can go up or down if you wish. So, one of the main aspects that we wanted to optimize was noise, and we tried to do so by optimizing the shape of the blades, which is one of the main components of the propulsion system. They're made entirely out of composite and are stiffer than steel and lighter than aluminum. And just to give you a sense of how strong they actually are, they can lift, or they've been designed to lift 125 kilograms, and they weigh less than 1.5 kilograms. So another crucial system actually that I wanted to mention about the rotor system is that it's actually a crucial safety measure for our device. So it relies on auto-rotation, which is a very fancy name for a very simple concept that I can demonstrate to you using a simple piece of paper. So if I just drop this, oh, sorry, didn't work very well. Yeah, so you see that it's converting its kinetic energy into rotational energy and slowing down in the process. And in the Hermes One, this is supposed to work in the same way, except that before touchdown, we can actually increase the angle of the blades and get an extra push to have a soft landing. So another very important aspect of the design, I'm just going to skip a slide, is that it has to be quiet. Helicopters and flying machines in general have been notoriously known for being very, very noisy. And a huge effort has gone into limiting their use around urban areas by moving airports to the outskirts of cities and restricting low-altitude airspace for use of these devices. But in personal air mobility, we want to move these devices to the urban areas, into our lives. So acoustic optimization becomes a real big issue to solve. So what you see here are not just pretty colors. This is actually a very high fidelity simulation of the flow around them. And this simulation has allowed us to get very accurate estimates of the noise produced by the device. And what you see here are the pressure fluctuations at very, very low RPMs, because otherwise they're just not visible. So the next question is, where does all this power come from? And it actually comes from the powertrain system. So the powerhouse of this device is a Propeller aircraft engine, and it was chosen because it has much higher energy and power density capabilities than current electric systems, and to be able to meet our 30-minute endurance requirements and at our power requirements, it was almost one of the only options. However, I must say that the team is currently looking at the new advents in electric technologies and is trying to make this device as efficient as possible so that zero-emission technology can be implemented in the very near future. So now, how does this power from the engine, which is capable of powering 187 households in the Netherlands, transferred to the rotors? Well, it's done through timing belts. The adjustable tension in these belts allows us to make sure that they're always operating at peak conditions, and they have many advantages over other transmissions, such as being more lightweight, requiring less maintenance, and being also way more reliable, and also being less noisy, because the meshing is between rubber parts. Now, the next big system of the device is the skeleton, of course. Skeleton is responsible for holding all the other systems together while being as lightweight as possible. The highlight of the skeleton is really the landing gear. Why? Because it's also a very important safety system. It uses the 4 C's that you can see, which are basically sandwich panels with carbon fiber on the outside and honeycomb on the inside. And this is inspired by Blade Runner designs, which use very similar physics to their advantage. So in this case, they have to absorb the energy of the impact of each footstep of the runner so that they don't feel the impact on their limbs and get injured. And instead it stores that energy in the material by creating a deflection. So this ability combined with a dampening system really allows us to have a landing gear that can absorb a huge amount of energy. So much, in fact, that even on landings of 12 Gs, we can reduce the number of Gs to 3, which is what the pilot would feel. So the next aspect to talk about are control systems, of course. Rotorcraft are well known for being very hard to control. And in conventional helicopters, all the controls are bundled together in the rotor hub. This makes them incredibly complex and introduces many single points of failure. Moreover, they also rely on many pilot inputs. So a pilot of a helicopter has to use all 4 limbs to control the device. And you can imagine how much training that requires. So in our quest to design a device to be used by everyone, we obviously wanted to simplify these controls and make them easy to use so that anyone can really fly this device without any training. So due to the experimental nature of the control systems that we've been working on, we've been designing 2 interchangeable control systems which we can easily swap out, and we're going to be testing simultaneously. The first one is the ducted fan control system. This basically relies on 2 electric ducted fans at the back, which are able to tilt to produce all the attitude control that we need. So if you're in hover, for instance, and you need to roll, then it's easy as just doing that. You create a force couple and you get a roll moment. If you need a yawing moment, you do something very similar. And the last rotation that you saw is the actual speed that they can rotate at. So this shows how fast reaction times with this system can be. So if there's a wind gust or something, this system can react automatically and very quickly. So this system has actually been tested, or the concept has been tested by companies like Lilium as well, which have integrated tiltable fans in their design. And they've tested it in a semi-autonomous device, which shows that there's a lot of potential for having active control systems that require really no piloting skills. And the last thing to mention about this device is that it's fail-safe. So if there's any problems with any of the fans, the pilot can just turn them off and he'll immediately go back to hover due to aerodynamic moments, even if he's in forward flight. Now, the second control system is one we're really, really excited about. So we thought, okay, the pilot is about 1/3 of the mass of the vehicle. Surely we can use his CG to do something useful, right? Like, if you go on a bike and you have to take a turn, you probably don't notice it, but you're using your center of mass to help in the maneuver. So what we're going to do now is we're just going to remove the side fans and the batteries with them, and then we're going to put a control surface in place instead of the side fans. So what we're going to do now is shift the seat of the pilot and get enough control, get rolling and pitching moments from that, and a yawing moment from the control surface at the back, which basically uses the downwash from the rotors to produce a force which can yaw the vehicle. And we've shown, according to our calculations, that a shift of just 10 centimeters of the seat of the pilot is enough to propel us to the forward speeds we need. So this has a lot of potential because it's a very elegant system. It's very exciting to fly, we think, and very intuitive as well. So that is really the goal, to build an intuitive, inherently stable, high performance and quiet device. You can call it a flying Segway. Aside from facing all these technical challenges, we've also been facing many logistical ones. We've made sure that every nut, washer, bolt, or any other component in the device is either manufacturable by us or directly purchasable. And this is crucial because we have very ambitious timelines, which we're ready to meet. So we're not relying on a magical technology or something to take off the ground. We're really ready to fly in a few months. So this is the future that we envision, and this is the Hermes One. Thank you very much.
Thank you, David, for showing us the engineering components of the device. So in the past 6 months, we have come so far from a bunch of loose ideas to hopefully starting our building phase next week and definitely throughout the summer. It's also our plan to have our first test flights at the end of this year, and in 2019, our first manned flight. We're looking into, as David said, the sustainable alternatives for our propulsion system, and we're keeping track of how the technology in the electric propulsion field develops. And we intend to improve on it as we go and as technology goes with it. To bring personal air mobility to everyone, we will need support from government, communities, and individuals like you. So we've started a fundraising campaign to help us build our landing gear. And for more information, you can check out our website, talaria.aero. To bring personal air mobility to everyone, it is also important to dream and to help us dream as well. Together, we can do this. I would also like to thank our current sponsors, Festo and Lilium, for joining in this dream with us. Ladies and gentlemen, thank you so much for coming tonight.